Hi class, we are on the last section of chapter 11. This is section 11.6, polar equations of conics. So what we're going to do here is we're just going to relate our conic sections to our polar equations. So when we covered polar equations back in chapter 9, we talked about our conics a little bit. We really talked about circles, and we kind of talked about ellipses as well. Because in polar equations we use, sines and cosines, so it's very, very easy to stretch our x-axis or our y-axis to get an ellipse. However, a hyperbola is a little bit different, and a parabola is definitely a different type of equation. So let's go ahead and get started. So conic sections are much easier to describe using polar equations. They're easier to rotate around an axis. They are easier to shift, basically. So it's a lot easier to talk about these things when we're talking about polar equations. So again, one of the main uses is that, or main benefits, is that if we have a conic that has a rotation of axis, we can just plug in that rotation into the angle for sine or cosine. Okay. In order to study our conic sections, let's start with the parabola, just like we did at the beginning of this chapter. The parabola is kind of the easiest, most basic conic section for us to study. If we remember our relationship for a parabola, we know that the distance from the directrix to a point is the same as that point to the focus. And we talked about that same thing in relation to the ellipse. Although an ellipse doesn't have a directrix, we did talk about what's called the eccentricity. So when we talk about conic sections in polar coordinates, the eccentricity is a very, very, very important thing. So remember what we talked about before, that when the eccentricity is close to 0, then you're very much more of a circular sort of figure, right? Because the focus is very close to the origin, to the center. When your eccentricity is close to 1, but less than 1 still, you're a very stretched out oblong ellipse. When you're equal to 1, that's when you have a parabola, because that's defined as the distance between the focus and a point over the directrix to a point, right? Because those are the same value. That's actually your C and your A, and that is why you are 1. And for when you're larger than 1, you have a hyperbola. So we're really going to focus on that right now, okay? So we know for parabola that the distance between my point, any point on this parabola, we'll just say it's here, and the focus is equal to that same distance from that point to the directrix, okay? The eccentricity of a conic is always going to be defined as this distance, right? So we know that for the hyperbola and the ellipse, it was C over A, which we'll get into in a second. Here, we're talking about it as ratio, the distance from the focus to the point and the point to the directrix. Okay. So if the eccentricity is 1, then we know that our conic is a parabola. If it is in between 0 and 1, then our conic is an ellipse. And if it's more than 1, then our conic is a hyperbola. So let's look at the triangle that's created by F and P. Okay, so on the ellipse, it's easy. On the ellipse and hyperbola section, we saw what those triangles were. More so on the ellipse. For this one, we're going to be looking at this right triangle that's created. Okay, we're going to use that to talk about our eccentricity. So we're going to look at the triangle that's created by F and P, okay, which has this shape, right? Focus to our point. This is that difference in height between the focus and the point, and then this is the difference on the x-axis in this case between the focus and the point. So again, that's this right triangle here. This is what we're analyzing. Okay. So we know that it creates some angle. This distance in x is r cosine theta. This height is r sine theta, and we're going to consider this as a length of r. So my height here is r sine theta. the distance from this point to the directrix, okay, so this is my r sine theta, and then I have 2p. So this distance from y to L, right, the directrix, that's the r sine theta, and the 2p, right, so that's 1p and then 2p, because each distance here is a distance of p. From the directrix to the vertex is p, and the vertex to the focus is p. So that's r sine theta and p. Okay. So the distance from p to L is this difference in height plus the distance from the focus to the directrix. So we know that the eccentricity here is the distance from F to P and from over P to L, and I can just substitute in my values. So here the distance from P to F is R, and the distance from my point to the directrix is r sine theta plus 2p. Now remember that polar equations are r of theta, right? So we want all of our r's on one side of the equation and all the theta stuff, everything else basically, on the other side of the equation. So as it stands, I have a mixture of r's and thetas, right? R's and everything else. So the goal is just to have r on one side. So what I'm going to do is I'll clear the denominators. Okay, so I have a little bit of everything on both sides. From here, I want to multiply out this e. I want to distribute this e. And then I'm going to subtract this term that has r onto the other side. So I can get all of my r's together and keep everything kind of separate, right? And now that it looks like this, I have a common term of r, so I can factor that out. And now that I've factored out my common term, everything else I want to get rid of, so I divide that on both sides. Okay, so now I have r equals some function of theta, right? And when my equation is a parabola, this eccentricity is equal to 1. So when I have a parabola, this will look like 2p over 1 minus sine theta, because e is 1. Okay, so this is the equation of a parabola. Remember though that we're talking about all conics. Okay, this value that I have here, 2p, that's the distance from my focus to the directrix, right? Because I go directrix, 1p is the vertex, another p is the focus. So 2p is the distance from focus to directrix. Only parabolas have a directrix. The ellipse doesn't have a directrix, a hyperbola doesn't have a directrix. So it doesn't really make sense to keep 2p here, because there is no p in an ellipse. There is no p in a hyperbola. We want to kind of generalize this so that we can use this for all of our things. So what we're going to do is we're going to get rid of this p. Really, we're going to get rid of this 2p, and we're just going to call it d. D will be the distance from the directrix to the focus. That'll be easier for us to use, because all of our things have a focus, okay? But not all of them have a directrix. So in this case, that's what D is going to represent. In our other conic sections, D will represent something else, okay? So if we change this sign value, okay, into a plus instead of a minus, our function will just demonstrate some symmetry, and it'll flip across the polar axis. So remember, the polar axis is what we call the x-axis, right? So our parabola will just flip and go negative, basically. Instead of being concave up, it'll be concave down, or vice versa, okay? If we change sine into cosine, then our graph is going to align with the polar axis instead of the theta equals pi over 2 axis, right? So when it's sine, it looks like this. It's right side up, okay, regular. Remember, pi over 2 line is the y-axis. So if we replace sine with cosine, it'll flip and it'll be along the x-axis, or otherwise known in polar coordinates as the polar axis, right? So cosine, remember cosines are always x's, so if it's a cosine instead of sine, its axis of symmetry is on the x-axis or the polar axis. Since we have sine, remember sines are y's, it has an axis of symmetry on the y-axis, okay? So remember we said that the eccentricity is what determines the type of conic that we have, Okay, so for a parabola, we will have an equation that looks like this, right? E times d. The distance is the length between the focus and the directrix. Okay, so it'll be e to the d, 1 minus e sine theta. If I have a positive sign here instead of a negative, it flips it across. Okay. If I have a cosine, it goes in this direction. And if I have a positive cosine, it goes in the other direction, but still centered along the x-axis. Okay, so these are the generalized formulas for a parabola. Okay, they generally will take on this shape. And that's, again, E should be 1 here. Okay, the eccentricity tells us what the shape is, so it should be a 1 for E. So let's just talk about this general, right? So a conic is represented as a polar equation if it has the form E d over 1 plus or minus E cosine theta, or R equals E times d over 1 plus or minus sine theta. So if you remember 10 seconds ago, that's what these look like. Okay, all of our conic sections look like this. It just depends on what our value of E is. If E is 1, it takes on this shape. If E is, I don't know, let's say 2, then we're going to have hyperbolas everywhere that follow the same sort of symmetry. Okay, if E is 1/2, we're going to have an ellipse, and it's going to follow the same sort of symmetry as well. Okay, sine will mean that your major axis is along this axis, right? Cosine means that your major axis would be along this axis. Same with the hyperbolas, right? If you have a sine here, your transverse axis would be along y, and your and if it's cosine, then your transverse axis is along x. So the sine and cosine is really what determines what's going on. And we'll look at all these cases independently. Okay, so d is a distance from the directrix to the focus, or c minus l. Okay, in the case that we well, the focus is at c, right? And e is c over a when the conic is centered at the origin. So R represents a parabola if E is 1, and the directrix is orthogonal to the axis of symmetry, meaning that it forms right angle. Remember, orthogonal means perpendicular, okay, which we already know is true. Axis of symmetry, right angle to that line, right? Directrix has a right angle to the axis of symmetry. D is equal to 2p, where p is the distance from the vertex to the focus. And this is all for parabola, right? All of this right here for parabola, these two lines is what we're talking about, okay? If we have an ellipse, then the directrix is orthogonal to the major axis. So we never draw the directrix, but there is still one there, and it lies outside of the vertex the same way, right? So an ellipse you can kind of think of having as like two directrix, right? And that's why it's kind of like two parabolas facing each other, if we think about it in terms of polar coordinates. Okay, so the directrix is orthogonal to the major axis, and if it's a hyperbola, then the directrix is orthogonal to the transverse axis. Okay, so let's do a couple of examples. Consider R equals 5 over 2 plus 3 sine theta. Now, remember what I always say. If our equation does not look like an equation that's easy for us to pull stuff out of, like this, okay, then we manipulate this so it looks like this. This is 2 plus something, okay? That's not really a big idea, big problem. It kind of is, actually. So we would like this to be a 1. This is a product of something, and whatever number is multiplied times our cosine or sine is going to be our E. So I know right away that E is 3. I also know that, actually I don't know that it's E. I'm going to have to pull some stuff out here first. Okay. So again, first we want to put this in a standard form. So really what I want to do is I want to pull out this factor of 2 before I try to find what E is. So I'm not going to say that E is 3, because that's going to mess up what I have here. I need this to be a 1. So I'm going to pull out my 2 first. Okay. So I'm going to factor out a 2. So this will be 2 times, this will be 1/2 times 1 plus 6, right? But pulling out a 1/2 here is going to help me, and that's going to change my numerator. Okay. So once I can pull this out and turn this into 1, it'll be really easy to figure out what E is because I pulled out that factor. Then I know it's multiplied times my cosine or sine, right? So we're going to divide everything by 2. Okay, top and bottom, or I could just keep the 1/2 on bottom, but then that won't be helpful. I would still need to simplify it. So I can just divide everything by 2. It's the same thing. That tells me my eccentricity then is 3/2 or 1.5. Okay. It's larger than 1, so that means that this conic is a hyperbola. Okay. So E times D is going to be 5/2. I know that E is 3/2, so that means I can find D rather easily. Okay. So D is 5/3. Okay. So we have our sine graph. It's orientated top to bottom, right? It's on the y-axis. So the transverse axis along the x-axis. I'm sorry, y-axis because it's on sine, right? We have a sine value here, so that's telling us where the transverse axis is. So if we wanted to find the vertices, then we have to use this information, right? We know the vertices are going to be on the pi over 2 line, okay? Because sine is y, that's where they're going to be. So what I would do then is, in order to figure out what my vertices are going to be, I need to remember that the pi over 2 line is actually 2 values. It's pi over 2 and 3 pi over 2. So I'm going to plug both of those in so that I can find my values, right? So that's where my hyperbola will intersect on the pi over 2 line. Okay. So I'm going to have theta is pi over 2. Plug that in. Okay. So I know I get 1 for that. So that turns into 5 over 2 plus 3. And so for this, instead of using this form, I'm just going to use the original form because it has whole numbers, right? It's the same equation. So 5 over 2 plus 3, which is 5 over 5, or 1. So I know that one vertex is at pi over 2 and a positive value of 1. Okay, that's the radius. So that's the first vertex. The next vertex is at 3 pi over 2, so I plug that into here, and I get negative 1. So this will be 5 over 2 minus 3, right? So that'll be 5 over negative 1, or negative 5. So that tells me that I have a second vertex at negative 5 for the radius and an angle of 3 pi over 2, right? But remember how this works, okay? So I'm at a location of 3 pi over 2, which is negative 1, and then I move in a radius of negative 5, right? So that gives me a value of 5 pi over 2 in polar coordinates, right? So remember, I'm down here for my angle, and then I go negative 5 from there. So I'm actually going positive 5. So that tells me that this is my first vertex, this is my second vertex. I now know where my center is. My center is the halfway point between 1 and 5 along the pi over 2 line. So add those together is 6, divided in half is 3. So my center is at 3 pi over 2. So that tells me that my A is the distance from 3 to 5 or from 3 to 1, which is 2, right? So my transverse line is the length of 4. My value of A, if I was to put this into regular standard rectangular coordinates, is 2. So remember my eccentricity. Okay, my eccentricity is 3 over 2. That A value is 2. So that coincides, which tells me that my C then has to be 3, because my eccentricity, remember, is always C over A. And since the A value that I have here aligns with the eccentricity 2, I don't have to do any math to find C. Okay, I'm going to anyways, right? But I know that C is C over A. So I can find C by going E times A, which in this case, A I know is 1/2 of 5 minus 1, which is 2, as I said before. So C is 3. Okay, so I did the math just in case we need to see that, but it was very, very clear here that the A value that I had, okay, from finding the distance between the center to one of the vertices, was 2. And so since that matches up, I don't have to make an equivalent ratio. I can just use this value, okay? But if I needed to solve it, right, just in case you guys need to see how we would do that in case it didn't work out, this is how we would do that, okay? So I have A, I have my C value. If I need to find B, I can find B for that central box, okay? So I know the location of my vertex, my foci. My foci have a distance of 3 away from the center. So that would be 6 pi over 2, right? And then going in the opposite direction would be at 0 pi over 2. So I have my foci, I have my vertices. That's really all I need. If I need to find my my asymptotes, my slant asymptotes, I just need A and B. So I have enough information to find B if that was the case, right? But I can use this information to find my foci. So I add 3 to the center, and then I subtract 3 from the center. So that gives me my foci, okay? If I need to find my value of B, I can solve it by using the formula that I have for a hyperbola. B squared is equal to C squared minus A squared. So we know that C was 3 and A was 2. So 9 minus 4 is going to give us 5. So B is square root of 5. So we have all the information that we need in order to graph our hyperbola. We can find the slant asymptotes, we can find the central box, we can find the foci, the vertices, we know the length of the transverse axis, all of that stuff. Okay, so here we have our graph in polar coordinates. You see our axis of symmetry is the line pi over 2. We have at a distance of a radius of 1 our first vertex, and 1, 2, 3, 4, 5 for the second vertex, 6 for the foci, and the center for the other foci. Okay, we can easily rotate a conic by an angle of phi in the counterclockwise direction. Okay, so counterclockwise means we go opposite the direction of a clock. Okay, using polar equations, all we have to do is subtract it from our angle theta, okay, in our equation. If we want to go the other direction, then we would just put plus theta because that represents a negative angle. Okay, so if I need to rotate by phi, I can do my rotation of axis very, very, very simply here. So that's one of the benefits of using polar equations for my shifted conics.